Good morning, everyone. Let us start with today's session. Okay. In the previous lecture session, we had seen how to design the control logic gates associated with any particular register, memory, flip-flops, bus, or ALU. Okay. I'll quickly scroll through the contents which we had already studied. Suppose you are asked to design the control logic associated with AR. So what was the step that we did? We first identified the instructions which changed the content of AR. Okay, so these were the instructions which we had identified from the list of instructions which we had already studied: memory reference, register reference, IO, fetch, decode, and interrupt. Okay, so from all these list of RTL statements which we had noted down for execution of different instructions, we identified the instructions that changed the content of AR. Okay, here in the first statement, PC to AR. So this is the first statement which is changing the content of AR. Similarly, this is another one which is changing the content of AR. Okay, so what we do is we first identify all the instructions that change the content of AR. So these are the instructions. Now from this, identify the instructions through which the content of AC is loaded, that is PC to AR. So we need to load AR. IR 0 to 11, we are loading AR with some value. M of AR to AR, so we are loading AR with some value. So these three instructions, through these three RTL, we are loading some data into AR. Okay, so these three would be associated with the load input of register AR. We know that every register has three main inputs, load, clear, and increment. So what we will do is we will associate these three control functions with the load input of AR. Similarly, this is the instruction which is clearing AR. So RT0 is to be provided to the clear input of AR. Only when R and T0 both are 1, the clear input of AR register will be 1 and hence the AR would be cleared. Similarly, D5, T4 would be provided as an input to the increment pin of AR. So when D5 and T4 both are 1, AR would be incremented. Okay, so this is how we designed. So this is load, clear, and increment. Okay, and if you see, do we have a figure here? Yes. So if I have a register AR, connect the first three control functions of the first three instructions to the load, D5, T4 to increment pin, and RT0 with that, with the control gates associated with a particular register, flip-flop, ALU, or memory. Let us now try to solve some more examples based on it. Okay, I think this is example 5.21 from your textbook. We are asked to identify the control gates associated with PC, the program counter in the basic computer. Okay, we will follow the same method as we did it for AR in the previous lecture session. So now what we need to do is, if I want to design the logic, if I want to design identify the control gates which are associated with PC in basic computer, we will be doing it. We'll first identify all the instructions from the list. Now see, every time you will not be having this list in front of you, okay? You need to remember these instructions, or you recall step by step which are the steps involved in each and every memory reference instruction, register reference instruction, IO instruction, yeah, fetch, decode, or interrupt cycle. Okay, so from this, let us first make out the steps. First identify the instructions that are changing the content of PC. Okay, because we have to design the control logic associated with PC. So this is the first one. R-T1. It is changing the content of PC and incrementing it by 1. Next, RT1. It is clearing the content of PC. RT2 again PC plus 1. So it is incrementing the value. Then check where do we have PC on the left hand side? D4 T4, D5 T5. Okay. Then here we are changing the content of PC only when DR is 0. Okay, so how we can write here, what would be the control function? DR should be 0. You can take any variable z named zdr and make it 1 if dr is 0. And that will be providing as an input to our PC. Okay, we'll see how to do it. But yes, we are incrementing PC if at D6 T6 time, if dr is 0. Let us identify another instructions. Do we have any other instructions which are changing the content of PC? Yes, we have number of instructions. So at RB4, PC equals to PC plus 1. At RB3, PC is PC plus 1. But in this case, AC15 is 0. AC15 is 1. Okay, so we'll add these as additional constraints. Here, again, PC is PC plus 1. PC is PC plus 1. So identify all the instructions that are changing the content of PC. I have two more instructions here. Okay, so now we have identified all the instructions that are changing the content of PC. Okay, let us note them down. First one, you can keep your book open in front of you. First one was at R-T1. Okay, that is fetch fetch cycle. In the fetch part, we are incrementing the value of PC. Then during the interrupt part, RT1, we are first setting the value of PC to 0 so that we can go to the 0th location and store the return address. Okay, not return address but IO programs address. Okay, then at RT2,
This meeting is being recorded.
at RT2, PC is PC plus 1. Then it was D4 T4. PC is AR. Okay. Then at in D5 T5, these were our memory reference instructions. D5 T5, we were setting 1 BSA. Okay. Okay. At D6 T6, we were incrementing the value if dr is 0. So what we can do is we can set a flag zdr is 1 if dr is 0. Okay, so what we are doing is we placed an additional control zdr. If dr is 0, zdr is 1. So along with d6 t6, dr should also be 0 for carrying out this instruction. Now, SPA value instructions. That was RB4. Skip if accumulator positive. So, for accumulator to be positive, AC15 should be 0. So, can I write like this? RB4 AC15 dash. In this case, what I need to do? Skip if accumulator positive. So, PC is PC plus 1. Then, skip if accumulator negative. So, here I'll simply write AC15. If AC15 is 1, this instruction will be executed. Then RB3, skip if AC 0. So again, similarly, can I write like this? ZAC is 1 if AC equals to 0. So I took 1, 2 additional flags. Okay. In this case also, skip. So PC is PC plus 1. Then what we need to do? RB1 E dash. Skip if E0. So PC plus 1. Then the skip on input flag, skip on output flag. So those instructions were PB9 FGI. FGI means if input flag is 1, skip. And PB8, skip on output flag. Okay, so we identified all the instructions. See, all these instructions are incrementing the value of PC. Okay, all these instructions. These two instructions are loading the content of PC. And this instruction is clearing PC. Okay, so now what we will do is, we'll simply design the circuit where this is my program counter, this is my load input, this is my increment input, this is my clear input. So you have different instructions. So in load input, take OR of all the instructions that we had identified here, wherever PC was loaded with some value. So D4 T4 and D5 T5. So what we will do is, we'll simply in the load input of PC, we will provide D4 T4 and D5 T5, or of these two. Okay, because these are the two instructions which are loading content into PC. Increment, you have number of instructions. So identify all those instructions and take OR of that, all these PC plus 1 value instructions. Okay, and RT1 is clearing PC. So here in the clear input, what we'll do is, we'll provide RT1. RT1, end of that. So now, once you have understood the concept, designing this type of control circuit for a particular register becomes very easy. Okay, in increment, you need to provide all the control functions which are incrementing the value of PC to PC plus 1. Okay, so this is how we'll be doing 5.21. That is, identifying the control logic gates associated with PC. Chalo, now let us see another example. We have already studied how to identify the control logic gates associated with read input of memory, read of memory. Okay, so if I want to identify read input of memory, what we were doing is, my M of AR should be on the right hand side. If I'm reading something from the memory, this is transferred like this. So this was read of memory, which we had already studied in the previous lecture session. Today, what we'll do is, we'll be identifying the control logic for write input of memory. Okay, so now if I want to identify the control logic associated with write input of memory, we will identify those instructions where we have M of AR on the right hand side. Whatever is here is written to the memory. Okay, so in this case, my M of AR should be where? It should be on the right hand side of the memory. So now let us see let us identify all the instructions where M of AR, how to select all? It's difficult. Anyways, so if I want to identify all the instructions that are on the right hand side of memory, first one is here. M of AR is TR. Then where do we have another one? M of AR is AC. AC to M of AR, PC to M of AR, DR to M of AR. Okay, so 1, 2, 3, 4. We found 4 instructions that are making changes to memory, M of AR. It means that are writing some data onto the memory. So now, after identifying these instructions, note them down. Okay, so when is M of AR updated? At RT1, M of AR is TR. So TR is transferred to M of AR. Then at D3, T4, AC is transferred to M of AR. Then D5 T5, sorry, D5 T4, PC to M of AR, and D6 T6, DR to M of AR. So these are the 4 instructions that are updating the content of memory, and hence for my memory I have 2 signals, read and write. What will I connect to the write input? RT1, D3, T4. Okay. Then D5, T4 and D6, T6. All these, in either of these cases 1, so this is an OR gate. If either of these is 1, enable the write input of memory. Okay, so this is how we will be designing the control logic associated with memory. If read input is asked, your M of AR should be on the right hand side of this arrow. If write input is asked, M of AR should be on the left hand side. That should be the destination, right? It should be on the left hand side of your RTL. So I think this is example 5.22 of your exercise. Sure. Now, the next question. So we saw one example for finding the control gates associated with a particular register. We saw how to identify control gates associated with memory. Let us take one more example. This is example 5.23 of your exercise. Here they have asked you to identify the Boolean logic of interrupt flip-flop R. During our lecture session, we saw how to identify the control logic for IEN and IEN flip-flop, right? So here, let us see how to design the control logic for interrupt flip-flop R. So all we have to do is, again, open this list, identify the RTL statements which are changing the value of R. So I have only 2 instructions which are changing the value of R. R is 1 here and R is 0 here. Okay, so I have only 2 instructions, 2 RTL statements which are changing the content of R. So identify those. Let us note them down. When is R set to 1? When do we set the flag of R to 1? We know that T0, T1, T2. During the fetch and decode phase, R is not changed. But after that, it checks IEN. If IEN is 1 and either of FGI or FGO is 1, set R to 1. This is the statement we had studied during the interrupt cycle. Okay, and then another one which we had identified was after our interrupt cycle gets completed at RT2, we again set back the R value to 0. Okay, so you are asked to design the logic for this. Now R is a flip-flop. Okay, so it can be any flip-flop. Let us take it as a JK flip-flop. R is a JK flip-flop. Okay, this is J and this is K. In this case, I want R to be 1. So what I'll do is I'll connect these inputs to J. So if this is 1, K would be 0. Why? Because we'll be connecting T2 here. Okay, and this thing T0 dash, T1 dash, T2 dash, IEN, FGI plus FGO will be connecting it over here. Okay, so if this is 1, J will be 1 and K will be 0. If J is 1, K is 0, R will be 1. So your R would be set to 1 in this case. And when T2 would be 1, so this T2 will go over here. If T2 is 1, yani J would be 0, K would be 1. In that case, R is set to 0, cleared. We know the property of JK flip-flop. 1 1 toggle, 0 0 no change, but J1 K0 output 1. J0, K1, output 0. Flip-flop is set here, flip-flop is cleared here. So this thing will connect to J and this will be connecting to K. In this question, they also said that minimize the number of gates. So if you want to minimize the number of gates, instead of taking this T0 dash, T1 dash, if I use this, I'll have to take 3 NOT gates. Okay, 3 NOT gates and then take AND of each. So instead of that, can I write it as T0 plus T1 plus T2 whole dash? Is it same? Yes, it is. So here this is a NOR gate and I'm connecting like this. So my gates are minimized. For this, so T0, T1, T2. This is IEN. Then we have FGI plus FGO, so that is OR gate, FGI, FGO, and AND of all these three. This will go to the J input of your JK flip-flop. Okay, and here T2. This is your R. So this would be my control logic that is associated with R flip-flop. Okay. So this is how for any gate given to you, if you are asked to identify the control logic for DR, DR is data register. So if you recall D0 T4, D1 T4, D2 T4, then D6 T4, D6 T5, all these are changing the content of DR. Here what we are doing is we are loading M of AR to DR in all these 4 instructions. We are updating DR to DR plus 1 in this instruction. So this input will connect to the load, this input will connect to the increment pin of our DR. Load, increment, clear. Let me show you the list of instructions. I told you D0, T4. Okay, here we are changing the content of DR. Here we are changing the content of DR. Look at all the instructions. Wherever we have DR on the left hand side, it means we are changing the content of DR. Note down all the instructions that are changing the content of DR. It may be some loading type of changing content. It may be incrementing the value of DR. It may be clearing the value of DR. We don't have any instruction which is clearing DR. So clear input would remain untouched. You will not be providing any input to the clear pin of DR. But yes, load input, you will provide the combinational circuit for these control functions. For increment, we will be providing D6, D5. Okay, so this is how we can design the control logic associated with any gates. Is the concept clear? I hope it is.